Hello, welcome to 5.2, Analyzing Graphs of Polynomial Functions and End Behavior. So now we're going to be using some graph properties that we've seen from the past, and we're going to be looking at polynomial functions and a few different things as we graph them, which is going to be in the next few sections. So the first thing we're going to note is what even functions are and odd functions. So even functions, typically for us, they have even degrees. So for example, 2, 4, 6, anything where the highest exponent is even, that's what we're going to consider an even function. And these have symmetry across the y-axis. Odd functions, as you probably have guessed, have odd degrees. So 1, 3, 5, anything where the highest degree is an odd number. These have rotational symmetry, 180 degree rotational symmetry. Okay. I'll kind of point out this idea later on. It's not anything you're going to have to stress too much about, but that's the definition for even functions and odd functions. Now, understanding infinity, we are going to be using infinity a lot to describe this end behavior. It's like how the shape of our graphs go in different directions. So note here, we have this function here, this polynomial that we're going to learn how to graph. It starts from the left side and it continues to go up, and then it kind of curves down, and then it curves back up, and it's going to end forever going up in that direction. So notice we also have two arrows here. We have one going to the right, one going up. This just shows us that as x goes to infinity, or as x approaches the right, this is what this means. Then f of x, or for us y, same thing, f of x is also approaching infinity because it's going up forever. So x goes left and right, so x as it goes to the right here, we are assuming forever and ever and ever it's going to continue all the way to infinity, going to go right. As it goes in that same direction, it's also going up in terms of the y value. It's continuing to go up the further right we go, right? Okay, so that's just our idea here is the infinity is telling us like the direction, and then we're thinking of x and f of x as our left and right or up and down. Here's a few examples that we're going to see. You guys have actually graphed these ones in the past. F of x equals x squared. We could go ahead and make a table for this one, but this starts at 0, 0, and it has the standard up 1 over 1 pattern, up over 2, up 4. Remember when we did these, I should probably write this out. So like 1, 2, 3, 1, 4, 9. And 0, 0 is our vertex, so that's why I started there. So then we'd have a point here, left 2 up 4, and we would also go over 3 up 9. So here's just a standard parabola. This is an even function, and it does have symmetry across the y-axis, meaning like this half is the same as this half. Now the end behavior here, like I was talking about before, notice this states as x arrow infinity. That means as x goes to the right. So if you want to practice this a few times, it's always going to be in this order. And then the second one, as x goes to negative infinity, that's just the opposite direction for x, which is to the left. Okay, so now we're trying to decide which direction is the f of x going for both of those. Now note on this one, whether I go to the left, it's going up, or whether I go to the right, it's going up. So now here, you just have to decide, are you going to put positive infinity or negative infinity? Since both of our tails, I call them, like the pieces that have the arrows, they end going up in both directions, this one's pretty easy. It's positive infinity for both. Now we're going to see on the next one, when we change this and we have a negative x squared, this is going to be the exact same graph, but it's going to go down. It's going to have the same pattern. Over 1, down 1, over 2, down 4, and then we'd see over 3, down 9, which is right here. I actually think I graphed this one wrong. I apologize. The points were here and here. I went one too many. But you get the idea. Same shape. All right, so again, as x goes to the right, so we're thinking right for this one, left for this one. Here, it looks in both directions. Whether I go to the right, it tends to go down, or if I go to the left, it also goes down. So then this is negative infinity. That's how we represent when the direction's going down. Now here we have x to the third. In this case, we're going to pick some different points for our table. So this one, we're going to have x and y. For these ones, I'm just going to give you the points, but we're going to do -2, -1, 0, 1, +2. Now, if you were to plug these points in for x, when you cube them, you would get -8, -1, 0, 1, and +8. So now we're just going to plot these so we can see how this looks. -2, -8 is down over here. -1, -1 is right there. 0, 0, 1, 1, and then over 2, up 8 is way up here. Okay, now I'm just going to connect my points. Note this one kind of curves a little bit, but it does go in opposite directions. We have one tail that's going down, we have one tail that's going up. So we just need to decide which order do we write those in. So since this is our right, this is our left, the one going to the right, if I'm thinking about my center, that's the part going this direction. That's where the tail is leading up. So that's going to be positive infinity. And then this one, as I go to the left, this direction, it's arrowing down. That's going to be negative infinity. Now this one here, I'm just going to quickly graph this, but it would be very similar. We would have the same x values. Our y values would just be negative, since it's negative x cubed. So we'd see -2, -1, 0, 1, 2, and then this would actually be +8, +1, 0, -1, -8. That's all it would change. So then we would have left 2 up 8, -1, 1, 0, 1, -1, and then over 2 down 8. And we would see this snake-like image. But now, you can probably guess the difference here. As we go to the left, it's going up, and as we go to the right, it's going down. So it's going to flip-flop our infinity signs. This one's going to be negative infinity. This one's going to be positive. Okay. Now, these are the 4 end behaviors. There's just a couple things that changed our directions here. It has to do with the degree, which you probably guessed when we had the even degrees. Note that both of them went in the same direction, either both positive or both negative for the infinity. The other thing that changed was when the sign in front. So if it was positive here with the even, they both went up, and when it was negative, they both went down. Whereas with the odd degree functions, they both went 2 different directions, but the negative sign determined which way they were going to go. So we have a little chart here we're going to look at. So as when the highest degree is even and the leading coefficient is positive, as x approaches infinity and negative infinity, f of x has an end behavior that approaches, and there's supposed to be a line here actually. We'll fill that in here really quick. Oh, actually, I remember why we had that. They both are going to go to infinity on this one. Here, they're both going to go to negative infinity when they are both negative, because this is the same for both here. Let me just explain that one more time. So even functions are when we have like 2, 4, 6, anything with an even degree. Since they have the same end behavior in both directions, they're either both going to go to infinity or both going to go to negative infinity. The odd ones like 1, 3, 5, those start with the same end behavior as it approaches infinity and negative infinity. So we want to think about this one. This is when it's positive. If we go back up to our example here, where we had an odd positive, it went to infinity and then negative infinity to the left. Okay, so notice these match up. When it's negative, it's the inverse. Then it's negative infinity, positive as we go to the left. Okay, and feel free to use that chart if you need it. You'll get better with it over time. So now we're going to make a quick sketch and then describe the end behavior for some of these. So in this case, we are always looking for the highest degree, which here is 6. So the degree is 6. And then the leading coefficient, or the a value, a is -2, or a is negative. So if that happens, if we have a degree that's even and a negative coefficient, then we are looking up here, if you want to use the chart, that would be even, negative. So this is how we would describe it, and we can write this out here. So as x approaches infinity, x approaches negative infinity, you can go back and copy these if you need to, then f of x will go down because both of them follow the same direction. Here, f of x would go down. All right, now we're going to look at the next one. Here we have an odd degree because 5 is the highest. So I always like to list out the degree, which is 5, and that's odd. And then the a value here is 4, which is positive. So then if we go to our chart, we are looking for odd and positive. So here's odd, it's one of these two. Odd and positive would be this one. So then we are looking at this end behavior right here where they match up exactly. Let me just move this one over here really quick. So then as x approaches infinity, f of x approaches the same thing. And as x approaches negative infinity, f of x approaches negative infinity. Okay. Next thing we're going to talk about is turning points. A polynomial function has a degree of n where the maximum number of turning points is n minus 1. So for example, if the degree is 5, then the turning points, or I'm just going to put it like that, would have to be 4, 1 less than that. So identify whether each function graphed has an odd or even degree and a positive or negative leading coefficient. So for this one, since it's going 2 different directions, we know that the degree would have to be odd because odd goes 2 different directions. The leading coefficient. So as we go to the right, it's going up, and as we go to the left, it's going down. So in that case, it follows the normal end behavior, so this would be positive. Okay, this one, it looks like both of our tails are going up in either direction, so that tells us it is even. And since they are both going up, that would mean that there has to be a positive leading coefficient. So I'm just going to put that for this one. Here we are going 2 different directions again. Notice how this one though, as we go to the left it goes up, and as it goes to the right it goes down. So this is going to be the inverse. So this one is odd and negative. That negative is going to end going down. And you can always go back up to the chart if you need a refresher on that. Okay, next thing we're going to talk about, the local maximum, local minimum, and then there's the global maximum and minimums. So the local max is any point that the behavior of the graph is going up. It's like a hill or a top point. It's not the absolute maximum point that we might see, but it's any point on the graph that seems to have like a hill or a vertical height to it going up. A local minimum is more like a valley. It's a low point where we change directions. Okay? This is called a local and a global maximum. You can have multiple local maximums. The reason it's called a global maximum is because it's the absolute highest local maximum. It's higher than this one we see over here. Okay, so now for the graph shown, we're going to estimate the x-intercepts and any local maximum or minimum from the graphs. We really want to understand this because it's going to help when we're graphing just to kind of double check our answers and be self-assured that we're doing it right. Okay, so the first thing let's do, estimate the x-intercepts. So here I see 1, 2, 3, 4, 5, it looks like. I probably should have just circled those. Now when you're estimating, just do the best that you can. It does not have to be perfect. We're going to be pretty understanding here, but be reasonable. So it looks like we're counting by ones. This first point over here is just slightly less than -2. So I'm going to say that that one is -2.2. This one here next to it looks to be a little bit to the left of -1, so I'm going to say that's -1.2 or -1.1. Anything like that is fine. The middle one looks like it's exactly at 0. The one over here looks slightly to the right, so I'm going to say that it's 1.2. And then the last one, again, looks slightly to the right of 2, so we can say 2.1 or 2.2, doesn't matter. Now, the number of turning points, that's the number of local maximums and minimums that we see. So in this case, we probably should have left a little bit more room here, but that's fine. So the local maximums and local minimums of the graph, we do see quite a few of those. So let me write this down here. Local max. And when we're talking about the local max and the local minimums, we only need the y values. So we're just looking for the y values for these ones. Okay, so the local maximums are our high points, the hills. So it looks like we have 2 here and here. So this first one, and I'll even change my color here. Let's do those as the local max. That one looks like it's right at about 2.9 or even 3, if you want to say that. And the other one looks kind of towards the middle, maybe slightly above halfway. So I'm going to say that that one is 1.6 for the y value. Now the local minimums, let's change color here. That's these ones dipping down here. So I'm just going to go the inverse. I'm going to say that this one is negative 1.6, and I'm going to say that one is negative 3. Okay. Now the turning points, since we have 4 in total, 2 local max, 2 local mins, we have 4 turning points. The lowest degree, therefore, has to be 1 higher. If we go back up here to what we were thinking before, the number of turning points is n minus 1, so the degree would actually have to be 1 bigger. So then the lowest degree is 5, which makes sense too if we think about the number of x-intercepts. We have 5 x-intercepts, 5 solutions, 5 roots. Goes back to what we talked about before. Here's our next one. This one's a little bit smaller. Looks like we have an x-intercept of negative 4. Be careful on this one because we're counting by 2's. So we do want to be cautious on that. We got negative 4. Local max and our local min, again I'll change my color. We only have 1 local max, and that looks to be right at 4 for the height, and then the local min is just slightly beneath 2. You could say 1.9, or I'm going to say 1.8 since we're counting by 2's. Might skew it a little bit, but that's fine. So then the number of turning points that we have in total is 2, and therefore our degree has to be 1 higher than that of 3. All right, the last bit here is going to be to use our graphing calculator. I'm just going to use Desmos again since that's what we used in the last video. And Desmos is going to give us some accurate points for a lot of these. It's pretty nice. All right, the hardest part is just typing it in. Just be really careful as you're going through. You don't want to mistype anything. Okay, now I'm going to slide off a little bit here because I want to be able to see all of these points. And that's the nice thing about Desmos. It will give you like any point here that you want. It gives you all the x-intercepts exactly. It can give you the local max, and if you just click on it again, it'll like unhighlight those. So lots of information that we can see from this. So the local max, I'm going to start with that one. Looks like we have 2 of them, here and here. So let's just round those to just 1 decimal place. So negative 0.6 and 1.5. Oh, sorry, I'm looking at the x values. Look at the y values. 2.6 and 0.4. Now the local minimums, we got another 2 here and here. Look at the y values. So that means we're looking at the negative 2.4 and the negative 4.6. The x-intercepts, we have 1, 2, 3, 4, 5. I'm going to start with these 2. So this one, you can round that one to negative 1, negative 0.1, 1.2, now I'm looking back at the x values. 1.8. In the last one, we're just going to go 3. Not exactly there, but close enough. And then the y-intercept, we do see a y-intercept of 0, -1. There's only one y-intercept here, which makes sense. You can only ever have one y-intercept, otherwise it's not a function. Okay, and then we're going to just describe the end behavior. If I were to do that end behavior, hold on one second. On this graph here, I should have sketched it at the beginning. It's going up, and down, up, and then back up. Kind of a horrible sketch, I do apologize. But it gives us the end behavior that we need. So it's going 2 different directions, which means we have one each way. This one would be as x approaches infinity, x approaches -infinity. As it goes to the right, it's going up. So that means f of x is positive here, and then it would be -infinity for the second one. All right, last part. Sketch a graph of a polynomial function that has 3 roots where one of them is a real root, and then it gives us the end behavior. So real roots always touch the x-axis. Imaginary roots do not. So if we're going to sketch this one, it has 3 roots where one of them is a real root. That means the other 2 have to be imaginary because imaginary roots always come in pairs. So that means we can only cross one time. Also, we have to match this. So as x goes to the right, f of x goes down. So we got to go right. I'm just going to go R and D, right and down. And then this one, as it goes to the left, goes up. So right and down, left and up means that it's going to look something like this. Okay, and we can actually take that exact graph that I just did. Voila. Because we only touch one time, it matches the end behavior, you're good. That's not the only graph we could have done. There's an infinite number of ways we could have graphed that, but this one works here. Okay, the next one here, make my graph. This time we sketch a graph polynomial function that has 2 roots where none of them are real. So in this case, x goes to the right, and then this goes up. So this is right, this is up. This one's left, also up, which makes sense because we know even functions go the same direction. So basically, we just need something like this. We could even do a parabola. It has to have 2 roots where none of them are real. So we just can't cross the x-axis. So anything drawn above the x-axis would work, something like that. And that's it.